here is the next model. It's one step more complex. We have size and fur in the model, as you can think of them as two main effects. There's two variables in the model. The order does not matter, and there's no interaction between them. So take a stab at interpreting this one.
I have a question about this model. Since we're only looking at main effects, are neither of these controlling for each other? Is this like the equivalent of running each of these separately?
It is not, no. This is, this is what if I would refer to as the relationship between size and Bork's adjusting for fur, or the relationship between fur and Bork's adjusting for size, or controlling for. When people say controlling for or adjusting for in a regression model, they mean that the variables are included in the same regression model. And one illustration of that is that here, the size slope is negative 9.9.
Oh, right, the numbers.
And when I ran it by itself, it was positive 6.9. So it's definitely not the same as running it by itself. Okay, that's a good question. You want to take a stab at what it means conceptually?
So, I mean, I'm seeing a main effect of scruffy fur such that having scruffy fur leads to, what is it, like 32 less Borks than fluffy fur?
Yep. So the scruffy dogs are borking 32 fewer times than the fluffy dogs, but not
But isn't
overall, right?
When adjusting for size?
Adjusting for size is one way to say that, yes. So adjusting for is kind of sometimes confusing terminology. And one of the things I want to talk about today is what does that actually mean? It's kind of like within each size category is one way to think of it. The scruffy dogs are borking 32 fewer times than the fluffy dogs on average within each size category, rather than just overall. And maybe the way I was like intending to think about this is to focus on this big row. So give that one a try.
Big dogs are borking 9 times less than small dogs when adjusting for scruffy fur. But when we say adjusting for, does that have anything to do with what our comparison group is, what our intercept is here? Like what we're considering that group to be?
No.
Okay, never mind. In this, what is our intercept referring to?
You have a guess?
Well, the reason I brought it up was because would it have to be, this is probably wrong, but would it have to be both, like accounting for both small and fluffy?
So the intercept, you could think of it as an estimate of the Borks for the small fluffy dogs. Okay. But it's not the average number of Borks in the small fluffy group here. And I'll show you why in a minute, but without showing you exactly why, you can think of it as this model calculates the average difference between the big dogs and the small dogs within any given group. Now you can visually see that the difference between the big dogs and the small dogs is larger in the fluffy group than in the scruffy group, right? But we're not accounting for that here. This is just the average difference between the big dogs and the small dogs within the fur groups. And this is the average difference between the scruffy and fluffy dogs within the size groups. And so this is the expected value for the small fluffy dogs under that set of assumptions. I think that that'll become clearer after we talk about the interaction example to show how this is different from the interaction example.
Okay.
But before we do that, thinking about this -10, -9.9, what does that look like in the picture? I mean, it's like we already knew that overall the big dogs were barking more than the small dogs. That's what this model told us, right? Positive 6.9, highly significant. And you can see that in the plot. There's a lot of points here around 40 for the big dogs, a lot of fluffy points, and a lot of these scruffy dogs are small and they're barking infrequently. The overall average on the big side is slightly higher than the overall average on the small side. But now we're getting this -10. And what does that mean? It's not the comparison of these overall averages.
You see these blue dots with the small that are quite high, they're up near 70, and this blue dots for the big, and there's obviously a steep negative slope there. So we would say maybe the average, whatever the average difference is, like 20 or something like that, and or decrease. And then with the red small to red big, that is less steep, if not really steep at all. So it's taking like those two, one negative, one like maybe a tiny bit negative slopes, and it's finding that middle ground between the two.
That's definitely one good way to think about it. Yeah. What's happening is when I got this positive 6.9 here, it would be like if I handed you a pen and I said, you get to draw one line horizontally through this graph. One line that has to best fit these points. Where are you going to draw it? And you might draw it, somewhat upward sloping, because you have to, get close to these big clusters of points. Down here, I'm telling you, you can, maybe this is a bad analogy, and if so, you can forget about it after I say it, but you get to hold two pens in your hand. You don't get to move them separately, but you get to hold them a certain distance apart, and you get to draw once across, but you get to draw two lines at the same time, but they have to have the same slope. If you ever took like music class in secondary school and you had one of those things where you could draw a musical staff with 5 pieces of chalk all at the same time. And so
I'm not recalling what you're talking about.
It's like a fork with pieces of chalk at the end of the tines. And so you can draw lines on a blackboard, but the lines are parallel. You can't move the tines away from each other. So you get to build one of those, and then you get to draw across this graph once. So where are you going to draw the lines? Well, you're probably going to start off with your tines right around here, one up here and one down here, and you're going to drag it slightly downward, because that's how you'll come closest to the blue points and the red points. But it's still not going to be perfect, because really what you would like to be able to do is have those slopes be different maybe. But so far this model is not allowing that. So when we have the relationship between size and Borks adjusting for fur, what that means is that the slope of size has to be the same within each fur group, but I do get to move it up or down for the different fur groups. And suddenly that relationship is negative, because on average within these fur groups, the big dogs are barking less than the small dogs, even though overall on average the big dogs were barking more than the small dogs, because there's lots of small scruffy dogs who don't bark much, and lots of big fluffy dogs who do bark a medium amount. So this should maybe begin to illustrate why I created the fake data with different numbers of the different combinations of dogs. If they were all equal in all 4 of these groups, then size and fur would be uncorrelated, right? They would be uncorrelated. They're binary variables, but we can still talk about whether they're correlated or not. And right now they're correlated. Size is correlated with fur because big dogs are more likely to be fluffy. If they were uncorrelated, then including them in the same regression model would not change their slopes. So we wouldn't get this nice illustration of what happens when you're adjusting for another variable. When you adjust for another predictor variable, it's useful to the extent that the predictor variables are correlated, because it's like saying I'm adjusting for the association between size and fur when I'm using size to predict Borks.
So I have a question. kind of imagining if I was going in blindly as a researcher, and I originally just wanted like an additive model, but I wanted to like build the model. And so I was like, okay, I'm going to start with size because I think size is a more important predictor. But I also think fur is important, but I want to take into account the variance explained by fur and the correlation between the two. So let's say I do the first model, I see size like positively predicts barking, but then when I add fur into the model, I see that the slope of size changes and is suddenly negative. And I'd originally wanted to do an additive model, but is that a sign that the interaction is actually really important and that these main effects are going to be qualified by an interaction? And then that would
No,
give
not
me
necessarily.
Okay.
That's a good question. So we will have an interaction in this example, but not because the sign flips on the size slope.
Okay.
Because what we have here with size being negative, this is already an additive model. This one up here just isn't adjusting for the covariate.
Right. Okay.
So this model that we have here, if these like, say, big scruffy dogs were lower, then you could imagine that drawing our parallel lines would be perfectly adequate. The only reason we might want to make it even more complex still is that we think the slope might actually be different in the scruffy group and the fluffy group. And it's, in any given research application, it's sort of up to you how important that is, whether you actually care if the slopes depend on the other variable, or if it's enough just to have them be at different positions depending on the values of the other variable.
Okay.
Which is why I feel like why I do like the correlation table in the beginning, especially if I'm just looking at relationships between like two variables combined. I feel like that's why that can be really helpful. Is that right, Sarah? Like in a situation like this, we could do the correlation table between the three. You could see how they all relate. You know, I guess these would be point by serial correlations, but still not adjusting for anything. And then
like this.
Yeah, you can. So what was the first one we did? We did size with forks. Yeah, and it's positive, which is what we saw.
We see that it's different when we adjust for fur, and that may have to do with the fact that size and fur are so strongly correlated. Yeah, it is useful to look at a correlation matrix like this. This correlation between size and Borks is closely related to this analysis that we did. For example, they would have the same p-value if you're computing it using a traditional t-test like this. This slope is just in the units of actual Borks. And this one is standard deviation units on both variables.